So get our schedule pulled up here. We're going to spend another day on volume. We're also going to talk about arc length. And things that are coming up are the due date for project 5, which is the candy project. If you didn't get the candy project, make sure you get one before you leave, and I have candy for you too if you didn't get the candy. And then also project 6 is coming, right? But it's not officially assigned until after break, but I'm going to give it to you Wednesday just because I don't want you to be bored over spring break, right? You need something to do, so. Okay, so today we're going to study another technique for finding volumes of revolution. This is called cylindrical shells. And in the candy project, you're supposed to do half of your volumes of the candy using discs and washers, discs or washers, and the other half using cylindrical shells. So you can choose which ones you want to use, which technique. But so today is the other technique that you need to know to finish that project. So in this technique, what makes it a little different than discs and washers is that our slices, when we draw one typical slice and watch it rotate, we're going to make our slice parallel to, rather than perpendicular to, the axis of revolution. All right, so this chapter is all about applications of the integral. We've spent, this is our third day talking about geometric applications of the integral, finding areas and volumes. But we're also going to talk about physics, economics, and probability in the next several classes. When all is said and done, you're going to have a sheet full of formulas for a myriad of different settings in which integrals are an appropriate tool. And you'll use those formulas competently on the next test. So over the coming weeks, it's going to be tempting to just wait for me to finish the lesson and just like wait for the formula of the day. But I want to encourage you to really focus on understanding why the integral is an appropriate tool in all of these seemingly unrelated applications. Formulas will always come and go, and you can always just look one up if you need one. So don't sweat the formulas. Try to aim for comprehension. In almost every class, we will solve a problem before we even know the formula, right? So you don't really need to know the formula if you understand the basis behind it. One last piece of advice, this material tends to get going fast and furious, so try to keep up with the homework and the reading as best you can in the next couple of weeks. All right, so let's look at a little animation to try to wrap our brains around this shell method. All right, so here is the same picture we looked at last class, right? Trying to find the volume of the solid that's created when I take this pink area and rotate it around this dashed axis of revolution. So let's just see what happens if I rotate that one rectangle around the axis. So I've created this thing, and I'm calling that's what I'm calling a shell. Okay, I've created a shell, and then I'm gonna stack all the shells until I've rotated the entire region around the axis. Okay, and then you just add them all up. Okay. We can do one more demonstration here. Again, I want to rotate this region around this axis of revolution. So this time I'm doing it without the rectangles, just the region itself. That's enough. And then you can see the shells are like, we call this cylindrical shells or nested shells is the name of the method. Okay, so we'll do an example, and hopefully that will make things clear. Okay. So let's say I want to take the region between y equals x cubed minus x and the x-axis, this region that I've graphed right here. I want to rotate it about the y-axis, so I'm going to go around that way, about the y-axis. I want to find the volume of the solid that's created using the shell method. So in the shell method, you pick one representative slice that's parallel to the axis of revolution. So last class, we would have picked a perpendicular one, and this is a little different. We pick a parallel one. So my axis of revolution is the y-axis, so I'm going to pick a vertical slice, right? At a random x value, I pick this little vertical slice, and I'm going to watch what happens when I rotate that vertical slice around my axis of revolution. What's it going to look like when I rotate this around? What's the shape that rectangle sweeps out? Yeah, kind of like a pipe. It's got some kind of thickness, like a roll of paper towels or something, right? So I'm going to do my best to try to draw what we create here. Okay. And what's the height of this thing? Close. Yeah, because x cubed minus x is a negative value, right? Because it's under the x-axis. So when you're finding the height of a rectangle, you always do the top y value minus the bottom y value. So in this case, we would do 0 minus x cubed minus x. So I'll just label this 0 minus x cubed minus x. Right, the top y value minus the bottom y value. All right. When you have this kind of tube shape, if I wanted to find the volume of that thing, imagine I can take a pair of scissors and cut down one side of it and unroll it. Right? So that's like a tube, rolled up piece of paper. And when I cut down the middle and unroll it, what shape do I get? A rectangle. Okay, so let's draw the rectangle that results when I unroll this thing. All right, so my height is still the negative x cubed minus x. What's the thickness of that rectangle? Delta x, yeah. Yeah, and that was also the thickness of my tube of paper towels, delta x. Because this is at a location of x and its thickness is delta x. Okay. What is the length of this rectangle? 2 pi x. Yeah, it's actually the circumference of the tube, right? So when it was all rolled up, like this, it looks like this. And then when you open it up, the length of this rectangle was actually the circumference of the tube. Okay. True, but what's going to happen is we're going to let delta x go to 0 in the end, right? Eventually, we're going to take a limit as delta x goes to 0. So the fact that those two are different lengths isn't going to matter. Okay. So we're just going to call it x and sort of pretend that that distance is delta x is so small that it doesn't make any difference. Okay. So the length of this rectangle is going to be 2 times pi times x. It's the circumference of this guy. And this distance from the center here to the edge is x, right? It's that distance on my graph. Okay, so now I'm going to try to find the volume by stacking up a bunch of these shells. So let's just look at the volume of a single shell. That would be length times width times height, right? Because it's like a little box. All right, the length is 2 pi x. The width is delta x. And the height is negative x cubed minus x. Yeah. Yeah. Why not? It's from the center of the circle. Okay, so yeah, I just addressed that, right? I said delta x is so small, that tube is so thin that it doesn't matter that there's a little bit of difference. Like, I had to draw this showing the thickness, right? But in reality, we're going to let that thickness get so small that the distance from here to here versus the distance from here to here is like there's no difference at all. So we're just going to call both of them x. Does that make sense? Because eventually we're going to take the limit as delta x goes to 0. So that thickness is going to become 0 eventually. So we're kind of looking ahead to when that happens. They're both just x. Yeah. This rectangle that I drew right here is just so skinny, right? It's just so thin that the distance from here to here, right, is no different at all than the distance from here all the way to the other edge. Okay. So we're just calling it x because it's the thickness of that rectangle is just so small that we won't even distinguish that there's a difference from the inner to the outer. Okay, so now I'm going to stack these shells up. Yes. Yes. Thank you. Yeah. When you distribute that negative sign, you get minus x cubed plus x. Thank you. All right, so now I'm going to make these little rectangles, these little slices throughout my whole region. Rotate each one, right? And then I'm adding them all up, right? What's the smallest x will be when I take the smallest possible x value? 0. And what's the biggest x value? 1. So I'm going to stack up these shells from 0 to 1. These rectangles that I'm going to rotate are going to get stacked starting at 0 and going to 1. So the volume of my solid ends up being the integral from 0 to 1. And then I take all these pieces, 2 pi x times negative x cubed plus x, and then the delta x becomes a dx when you take the limit as delta x goes to 0. Right? And I've run out of room. I'll just go down here. Okay, so I'm going to pull the 2 pi out and I'm going to distribute the x. So this becomes 2 pi times the integral from 0 to 1 of negative x to the 4th plus x squared dx. take the antiderivative. So I have 2 pi times negative x to the 5th over 5 plus x cubed over 3, evaluated from 0 to 1. So this becomes negative 1/5 plus 1/3. That's what you get when you plug in the 1. When you plug in the 0, you get 0. Negative 1/5 plus 1/3. Two 15ths. So I have 2 pi times 2 15ths, which is 4 pi over 15. So in general, the formula for cylindrical shells method, when you make a slice parallel to the axis of revolution, is 2 pi x f of x dx, right? The 2 pi x was the length of the shell, f of x was the height of the shell, and dx is the width. Okay, so that's the cylindrical shells method. Next thing we're going to talk about is arc length. If you want to find the length of a curve from x equals a to x equals b, just how long a curvy thing is in the xy plane, you can take the integral from a to b of the square root of 1 plus f prime of x squared dx. So that's another formula of the day, and the derivation of the formula you're going to read through in the group activities. For now, we're just going to do a problem where we apply that formula. All right, so I want to find the arc length of y equals cosine x from 0 to 2 pi. How long is that curve? So the formula was the integral from a to b of the square root of 1 plus f prime of x squared dx. So in our case, we're going from 0 to 2 pi. Integral from 0 to 2 pi of the square root of 1 plus, my function is cosine x. I have to plug in the derivative of that squared. What's the derivative of cosine x? Negative sine. So I just put negative sine x squared dx. So this becomes the integral from 0 to 2 pi of the square root of 1 plus sine squared x dx. And then if you just put that in a calculator, so I'll just do math, function integrator. I want the square root of 1 plus sine of x squared with respect to x from 0 to 2 pi. Oops. Did I not close a parenthesis? Yeah, I opened the square root, I think. One more. Yeah, I think you're right. I got to close the square root. Yep. And then that probably just needs 1. Okay, so I opened the square root. I opened the sine and squared it. Close the sine, close the squaring. Yeah, that should do it. Okay, so I get about 7.64. It's different than what I got when I did this earlier. Make sure I'm in the right mode. Yep, I might not have been when I did it before. All right, so that's just plugging into a formula, right? And then I got one more formula for you. If your curve is given parametrically, you guys remember what that is from like a pre-calc course? Parametrically defined curve. You have x equals some stuff in terms of t, and y equals some stuff in terms of t, and then you plug in t's, and it gives you the x and the y's, and you plot them. Right? So this is something you covered in a pre-calc class. Definitely, if you took it here, you did. So the arc length for a parametric curve is the integral from a to b of the square root of the derivative of x squared plus the derivative of y squared dt. So here I have x equals 2 cosine t and y equals 4 sine t. So if you wanted to graph that thing, you would have to make a table of values t, x, y. You pick a bunch of t's, in this case 0 to 2 pi. Pick a bunch of t's in there, and then you get the x value and the y value, and you plot the x's and the y's. Anybody know what this is going to come out to look like if we were to just graph it? Remember from a couple semesters ago? Nobody? It's an ellipse, yeah. Yep, an ellipse. Good. So it's an ellipse, but we're just doing a plug and chug here. We're just applying a new kind of formula. So this is just going to be the integral from 0 to 2 pi, because that's what they gave me for t's. Those are my bounds, of the square root of the derivative of x with respect to t squared. So what is the derivative of x with respect to t here? Negative 2 sine t. Just take the derivative there. Negative 2 sine t and square it. Plus then we take the derivative of y with respect to t, just following the formula here. So I get 4 cosine t squared dt. And I simplify this 0 to 2 pi. This becomes 4 sine squared plus 16 cosine squared dt. And again, I'm just going to have a calculator do this for me. The function integrator, and my function is 4 times sine of x squared plus 16 cosine of x squared. Integrate with respect to x from 0 to 2 pi. Yeah, I do. I forgot to copy the square root. Thank you. All right, so second enter, pull this back up and put a square root in front of the whole thing. Oops, no. Square root. And then I got to close the square root before right here. There we go. $19.37. All right, so that's it for the demo for today. You're going to practice with some cylindrical shells and with some arc length formula stuff, and I'll be around to answer questions. All right, so looking at number 3, I'm not going to go through the whole thing of finding the arc length, but your hint is to rewrite that function using sines and cosines. Rewrite it parametrically using sines and cosines. So that function says y equals the square root of 4 minus x squared. If you square both sides and rearrange a little bit, you end up getting x squared plus y squared equals 4. And what does that look like? That's a circle with radius 2 centered at the origin. So quick sketch like that. Okay. So if I wanted to define this parametrically, the unit circle we define parametrically because every point on the unit circle is the x coordinate is cosine of the angle and the y coordinate is sine of the angle, right? So you can do the same thing for any radius circle. You just have to multiply by the radius to scale it up a little bit. Okay, so, and instead of using theta for the angle, we use t's. It's just sort of, I don't know, that's just what's done when you define things parametrically. You use t. Okay, so when I define this parametrically, I would say, well, the x coordinate of any point on this circle, just pick a random point, right? The x coordinate of that point, right, is going to be 2 cosine t, where t is your angle, right? And the y coordinate of that point would be 2 sine t. And then you just let t go from 0 to 2 pi, and that will get you a full rotation around the circle. So this is your parametric definition of the circle. Circle defined parametrically, and then you can use the parametric formula to find the arc length once you have it done that way.